You are listening to The Vocal Technologist. Spoken tech for your ears.
All right, let's just jump right in. If you spend your week wrestling with infrastructure, trying to squeeze every last drop of performance out of your systems.
Or, just keeping Kubernetes from completely imploding.
Exactly. Then this is definitely for you. Welcome to Tech Tuesdays.
Yeah.
We've looked at a fantastic range of material this week. It really covers everything from deep database optimization
All the way to the very real human side of open source work, the burnout stuff.
Right. And our goal today, pretty simple, really. We're cutting through the noise.
Yeah, straight to the engineering insights, the stuff that's actually changing how the best teams are thinking about scale and stability. And, if there's one big theme I took away from all this, it's stop focusing just on faster hardware. Seriously.
Right.
The huge performance boosts right now, they're coming from smarter architecture, especially smarter data handling, better query patterns. You have to realize the two biggest speed wins we're about to talk about, they didn't cost a cent in new hardware. Just, smart thinking.
That point is perfectly made by some of the numbers we saw. I mean, the scale of these optimizations is, frankly, it's kind of mind-blowing.
It really is.
Let's unpack this. Two really prime examples that should probably make every developer take a hard look at their queries.
Definitely.
Okay, first, ClickHouse. Log query scanning. They reduced it by 99.5%.
99.5, yeah.
That's not a typo. It's like, basically, they eliminated almost all the I/O waste. How on earth did they manage that kind of speed up?
It's a really clever solution, actually. It replaces something that was just fundamentally inefficient.
Which was?
So before, ClickHouse used what's called a Bloom filter skip index for these log queries.
Okay, Bloom filter.
But the problem in this context is that a Bloom filter isn't sequential. It doesn't know where the data is, just that it might be there. So the system had to scan almost all the data blocks just to check. Okay, so tons of I/O just to maybe find something. Maximum effort, minimum result.
Exactly. Terrible yield.
So if the Bloom filter was the problem, what did they replace it with?
They brought in this deterministic resource fingerprint.
Deterministic fingerprint. Okay.
Yeah, this fingerprint let them completely reorganize how the data was stored physically. They could pack logs for specific namespaces right next to each other on disk contiguously.
Right, so grouped together.
Exactly. So now when a query comes in for a namespace, it doesn't scan everything. It knows precisely where to look. They went from reading nearly 100% of the blocks down to just, 0.85%?
Wow, just by reorganizing the physical data layout.
That's the power of smart data organization. It minimizes that costly disk seek time.
Incredible.
Yeah.
But, you don't always have to mess with the storage layer to get these wins, do you?
No, definitely not.
Our second example is pure query optimization. And honestly, maybe even wilder. The Matrix Rust SDK team working with SQLite.
Oh, yeah. The 211x speedup. That one's a classic. 211 times faster. Throughput jumps from, 20,000 events a second?
Up to 4.2 million events per second.
It's staggering. When you see a number like that, you just know there was one single really nasty bottleneck somewhere.
Absolutely. And in this case, it was just a badly chosen SQL operation, a single query pattern.
What was it doing? What was causing that insane drag?
It was one extremely inefficient left join. They were using it to fetch metadata for chunks.
Okay, a left join. Seems common enough.
It is, but the way it was structured forced the database into these huge, unnecessary full table scans every time. It wasn't just slow. Sometimes queries took over a minute.
Ouch. So the fix was just rip out the schema and start again.
Nope, and that's the really cool part. They didn't touch the schema.
Really?
Yeah, they just stopped trying to make the database do everything in one giant complex query. They broke it down.
How?
Replaced that single left to join with two much simpler targeted queries, and then they handled the final data joining and processing in the Rust application code itself. Okay, so pull the complex logic out of the database.
Exactly. It's a great reminder, right? Sometimes the smartest architectural move is to simplify the database query and handle the complexity in your application layer.
Makes sense.
Now, connecting these kinds of performance wins back to, actual user experience, we have to talk about observability, how you measure this stuff.
Right.
You just can't understand your system's real performance by looking at simple averages. If you remember one thing from this discussion, focus on latency percentiles. P50, P95, And especially that P99.
The T99. That's where the real pain often hides, isn't it? That slowest 1% of requests that tell you something's really wrong.
That's exactly it.
Yeah.
Your average, your P50 might look great. Maybe it's 50 milliseconds. Awesome. But if your P99 is spiking up to 5 seconds, you don't have a fast system overall.
No, you have a system with a serious problem affecting a chunk of your users.
A major systemic flaw, yeah. The P99 exposes that hidden architectural friction. It shows you the worst-case experience. But getting those percentile numbers right, it's not just about counting requests, is it?
No, you need the right tools. Specifically, you need histograms.
Histograms. Okay.
Averages hide the distribution. They lie by omission. Histograms show you the whole picture, the spread of latencies. They pinpoint where the friction is happening.
And when you find that high P99 friction,
it often forces you to look beyond simple tweaks. You have to dig deeper into architectural changes. Things like fixing cold start problems, maybe partitioning your data differently, or implementing smarter retry logic like adaptive retries, maybe closer to the edge.
Right. It holds you accountable for those edge cases, those worst experiences.
Exactly. It makes you own the entire performance profile.
Okay, so speaking of complex systems and friction, let's talk Kubernetes, K8s. It's always changing, right? But sometimes the really crucial updates aren't the flashy new APIs. Sometimes it's about stability, about making things less painful to manage.
That's a perfect segue, actually, because Kubernetes 1.34 delivered a huge win for admins on exactly that front. Quality of life.
What was that?
The kubelet group driver from CRI feature, it's now GA general availability.
Okay, break that down. What's the simple benefit?
It means the kubelet that's the main agent running on each node can now figure out the right T-group driver automatically. It gets it directly from the container runtime, the CRI, like a containered or CRIO.
Ah, okay. So instead of manually setting it and hoping it's right.
Exactly. That used to be a common point of failure. Manual configuration, easy to get wrong, leads to weird node issues. Now it's automated, more stable, less human error.
Nice. Reducing that kind of config drift is always good, but there's a catch, right? A dependency warning tied to this.
A big one, yeah. Cluster admins really need to pay attention here. Kubelet version 1.36.0 is going to drop support for older versions of container.
Okay, so what's the action needed?
You absolutely must upgrade your container to version 2.0 or later before you upgrade your kubelets to 1.36.
Got it. So manage that dependency chain carefully.
Or you're looking at a potentially serious outage later down the line when things just stop working.
Right. Okay, so beyond stability, 1.34 also brought in something new for visibility, didn't it? An alpha feature.
Yeah. Resource health status. This is aimed at people running, fancy hardware like GPUs or FPGAs inside Kubernetes.
Specialized workloads.
Exactly. This is a big step towards standardizing how that hardware reports its health. It adds a new way for these dynamic resource allocation drivers, DRA drivers, to push health status directly into the pod's status field.
So like the scheduler or your monitoring tools can see directly if that expensive GPU is actually healthy and working.
Precisely. It gives you a standard direct line of sight, closes a pretty big visibility gap we had before for specialized hardware.
Makes sense. And as K8s itself matures, the ecosystem around it is moving fast too.
Oh, yeah.
We saw Grafana's K6 operator hit version 1.0. That makes running distributed load tests inside Kubernetes way easier.
Yeah, simplifies coordinating those big test runs.
Plus, for folks using Terraform, especially on AWS, Terraform agents can now auto-scale on EKS auto mode using the HTTP Terraform operator.
That's another big one for platform teams. Takes away that manual scaling headache for your Terraform infrastructure. Less babysitting.
Definitely valuable automation wins. But, we need to talk about a less positive development, something highlighting a different kind of risk.
We do. We need to pivot pretty sharply here and talk about a systemic threat that surfaced. It's about the maintainer crisis affecting the Kubernetes external secrets operator, ESO.
Wait, ESO? The tool lots of people use for managing secrets in K8s. You're saying it's in trouble.
It's currently frozen, basically on ice, due to really severe maintainer burnout.
Frozen how?
There's only one active maintainer left right now. One person.
Wow. For such a critical, widely used security tool.
Exactly. And the practical impact. Everything stops. No new features, no bug fixes, and critically, no security patches.
Oof. That's bad. What's the recovery plan look like?
It's sobering. The estimate is they need about 5 new, really dedicated maintainers. And just getting the project stabilized again could easily take 6 months, maybe longer.
6 months without updates or patches? for a core security component.
It really drives home the point that sometimes your biggest architectural risk isn't a bug in your own code. It's the critical open source piece you depend on that's just starved of human effort.
It's a chilling example of supply chain risk, but the weak link isn't malware. It's just people burning out.
Yeah. It makes you really think about every dependency. You have to ask, what's our plan if the handful of people keeping this alive just walk away?
Okay, let's shift focus a bit now. Let's talk about the platforms and the tools that developers are actually touching day to day. From the metal up to the config files.
Right. Starting with some hardware acceleration news, for teams doing macOS development, Amazon's EC2 M4 and M4 Pro Mac instances are now generally available GA.
These M4s, they're a pretty decent step up, right?
Huh.
Offering something like up to 20% better build performance compared to the M2 Max.
Yeah, and with up to 48 gigs of unified memory, it's a serious boost for iOS or macOS dev workloads running in the cloud. Good option to have.
Definitely. We also saw a really interesting architectural choice from Cloudflare. They talked about their serverless rate limiter and how they completely ditched Redis.
Yeah, that one caught my eye too. Replacing Redis, that's a big move.
Right. Redis is like the standard for caching and fast lookups. Why would a global player like Cloudflare move away from it for rate limiting?
Well, according to them, for their specific use case, global, high-traffic, edge-based rate limiting traditional Redis setups had issues. Latency problems, cold starts, especially when traffic spiked suddenly at the edge.
Ah, okay. And if your rate limiter is slow or inconsistent?
It's letting too much traffic through.
Yep.
Right, it undermines the whole point. So they switched to their own thing, durable objects.
Cloudflare, durable objects, what's the advantage there?
Strong consistency, apparently, and really low latency, like sub 5 milliseconds right at the edge globally. They basically traded the complexity of managing a separate Redis fleet for guaranteed consistent state using their serverless platform.
Interesting trade-off. Less operational overhead for the caching layer, more reliance on the platform's consistency model.
Exactly. A big bet on edge consistency.
Okay, while we're on infrastructure platforms, a quick but crucial heads up for Azure users. Phase 2 of mandatory multi-factor authentication.
MFA, yeah. It kicks in October 1st.
What does that mean practically?
This phase targets the Azure Resource Manager layer, so human users logging in to manage resources. You need to have MFA enabled. And importantly, you also need to update your Azure CLI and PowerShell clients.
Ah, update the clients. Why?
Because older clients might not support the MFA flows properly. If you don't update, you could get blocked from accessing the management APIs. So enable MFA and update your tools.
Got it. Good PSA. Okay, let's pivot now to the developer interface itself, starting with all the buzz around AI coding tools.
Oh, yeah, the AI assistants.
You had a specific take on this, suggesting we stop thinking of them as intelligent partners and use a different mental model.
Yeah, I think a better, more realistic way to frame them right now is as incredibly sophisticated compilers.
Compilers? How so?
Well, what do? They take imprecise, often ambiguous input, like an English language prompt, and they transform it into a precise output. Executable code.
Like a compiler takes source code and outputs machine code.
Kind of, yeah. Their real power isn't true understanding or creativity, not yet anyway. It's in that transformation. They're amazing at improving search, helping optimize boilerplate, accelerating tasks, basically supercharging existing tooling, not replacing the programmer's intent.
That framing actually connects really well to our last point about configuration.
Absolutely.
If these AI tools are taking English, which we just agreed is imprecise and ambiguous, and using it to generate infrastructure code or configuration,
then we need to be hyper-aware of the languages we use to instruct our systems, whether those systems are AI or just plain old automation. Meaning we need to start treating our configuration files YAML, JSON, TOML, whatever, like actual user interfaces. Because they're the primary interface between the human developer and the complex infrastructure underneath.
And if that interface is confusing or brittle or easy to mess up,
it kills developer productivity. It introduces errors. That's why you see alternatives like KSON popping up.
KSON?
Yeah, it's another configuration language, but it's specifically designed to be more intuitive, more resistant to common errors like YAML's indentation nightmares. It focuses on the human experience of writing configuration.
Reinforcing that idea that configuration needs to be designed for the person writing it, not just the machine parsing it.
Exactly. Treat config like UI. It shapes the entire developer experience.
So, pulling this all together, what's the big takeaway for you as you're out there building and managing systems?
Yeah, what's the bottom line?
Well, I think we've seen pretty overwhelming proof, haven't we? Massive performance gains. They're often hiding in how you access and handle your data, not just in raw hardware speed. That 211x SQLite speedup just from changing a single left join.
Exactly. That's the clearest possible sign, right? Focusing on elegant data interaction, smart architecture, it gives you exponentially better results than just throwing faster CPUs or more RAM at a poorly designed interaction.
It's about working smarter, not just harder or more expensively.
Precisely.
And thinking about that Kubernetes external sequence operator situation, the maintainer crisis, it really highlights a different kind of risk.
Yeah, a human element.
The biggest threat to your infrastructure might not be the latest zero-day exploit. It might be that critical open source cog in your machine that's just running on fumes because the community support isn't there.
It forces you to think about risk management differently. It has to include the sustainability of the communities you depend on. Are they healthy? Are they supported?
Really good point. Okay, so we kind of established that today's AI coding tools are like fancy compilers, taking imprecise input English and outputting precise code.
Right. The English to code compiler.
So if English is the unreliable, ambiguous input that can lead to potentially shaky infrastructure, here's a final thought for everyone to sort of chew on this week.
Okay.
What comes next? What's the next language we'll use? Not English, maybe, but something more precise, more structured. A formal language designed specifically for instructing these powerful AI systems to reliably build and manage complex infrastructure at scale. What does that language look like?
That is definitely something to think about. A new language for AI infrastructure generation.
Something for the road.
Yeah.
Anyway, thank you for joining us for this really interesting discussion today. Hope you found it valuable.
Yeah, great chat.
Till next time, keep building, keep optimizing.
Spoken Tech for your ears.